In the last lecture, we introduced Faraday's law and how Faraday's law can be used to explain the behavior of transformers and the development of a so-called transformer electromotive force, or EMF. In today's lecture, we're going to focus on motional EMF and how the motional EMF combines with the transformer EMF to yield a total EMF. So moving forward here, the motional EMF arises from relative motion between a closed path and a steady field. So this is very different from the transformer case because at least for the time being here, when we're considering the definition of motional EMF, we will assume the B field to be static. It is not time varying. And instead, the time varying nature of the problem arises from motion of the path within the static B field. So as an example, let's say we have a conducting bar, which is shown in this figure on the right, and we are moving this bar, like pulling it or some other means, through a static B field that is uniform over space. So having a look at the coordinate system here, the B field is in the plus Z direction, which is out of the page, and we're moving the bar to the right, which is in the X direction. So let's think carefully about what's going to happen in this situation. There are many free charges in this conducting bar, and let's for a moment assume that we consider a positive charge, and that positive charge is being moved to the right with some velocity u. So these charges are moving, and we know that because we're moving that charge in the presence of a magnetic field, there will be a magnetic force exhibited on that charge. And we know the value of that force. We'll write it down here. The magnetic force exerted on that charge, assuming it has a value Q, let's say this was Q, is U, the velocity of the charge, crossed with B, the field that we have here. So using the right-hand rule, we can determine the direction that this wants to go. So the U is to the right and the B is out of the page towards you. So the resulting force that's going to be exhibited on that charge is downward. Okay, that charge is going to want to be pushed downward. And you can see that this charge, when we place okay, so we have this force on this charge. And we also know that we can define an electric field, which we'll call EM, as the force per unit charge. This goes back to our fundamental definition of electric field. So if we take the force exhibited on the charge, this time due to a magnetic force, but a force nonetheless, and divide by that charge, that gives us an electric field. And this is simply the cross product of U and B. So you can see this is illustrated in the figure here. We have an electric field established within the conductor that motivates that charge to move. So, and we know that if we place the positive charge in an electric field with the direction shown pointing downward down through the wire, then that positive charge is going to want to move downward, consistent with the force that's being exhibited on it. This also means that since in a conductor the free charges are electrons, the electrons actually move upwards through the wire in this example and not downward. But let's keep it simple and talk about everything in terms of positive charges here. So this is the electric field that is established within the wire. We can now find a voltage associated with this by integrating the electric field over the length of the wire. So let's do that now. So let's find the voltage between the points 1 and 2. Using our previous convention for voltage, we'll define it this way, which requires that we integrate from the bottom of the wire, which is 2, to the top of the wire, which is indicated as 0.1 in the diagram, this electric field due to the magnetic force dot dl. Okay, notice there's no negative sign in this definition of EMF, which is consistent with our definition of EMF previously when we looked at transformers. So if we substitute in, we're going to integrate from 2 to 1 this cross product of velocity and the B field, and then take the dot product of that with dl. So we're integrating from 2 to 1, so our dl is pointed upward like this. This is the direction of dl, and now we can proceed to calculate this. So this is what we call this quantity also has units of volts, and so it is also an EMF, and we call this a motional EMF because it arises due to motion of a charge within a static magnetic field. So we will use the same notation we had the other day. We have a subscript EMF, just to remind ourselves this is from an EMF, and we'll attach a subscript here, M, for motion. You'll recall the other superscript was TR for transformer. Now, if we look at this integral on the left-hand side, here we only integrated over a segment of the wire, but we know that this current can only be motivated to flow in the wire if the wire was part of a larger closed circuit. So if we go back to this picture here, technically speaking, we need this a closed circuit completing this wire in order for a current to flow. Otherwise, if we just drag an open wire like this through the B field, it's just going to cause the positive charges to accumulate at the bottom of the wire and the negative charges to accumulate at the top, but there won't be any current. We can only motivate the current to flow if there's a closed path. This is consistent with what we said about Faraday's law in the last lecture. We can only induce an EMF in a suitable closed circuit. So we're, in essence, when we're looking at this bar here, we're zooming in on part of a closed circuit. So technically, this integral that we wrote on the left-hand side of the motional EMF should be defined as a closed contour integral, because we would have had to integrate over the rest of the circuit as well to find this motional EMF. So this is the cross product of U and B dot dl. That is the motional EMF. So this is our definition. You can see that the expression for motional EMF is very, very different from the one that we had for a transformer EMF. Okay, so moving forward, let's have a look at a more practical example of a way of creating a closed circuit and making a sort of generator from this motional EMF. And that is shown in this picture here. So consider a situation where we have a number of bars here. So let's say these two bars on the top and the bottom, these are fixed. We just place them there, they don't move. There are also some conductors here that connect the bars that aren't in motion to a resistor. And that resistor is going to serve to dissipate the power that's generated by this electromagnetic generator. Then we're going to place another bar on top of these two rails, essentially, that we have on the top and the bottom. And this orange bar will be dragged across from left to right at a velocity u. So remember, the top and the bottom bars aren't moving, but they do have contact with this moving bar. So we're dragging this moving bar. It remains in contact with the two rails on the top and the bottom. And so we do have a closed circuit in this case, but this bar, this orange bar here, is the only element of this problem that is in motion. This is to simplify things a little bit. So we have this rectangular loop, and so the width of this loop is constant because the distance between the top and the bottom rail is not moving. But the length of this rectangular loop, which is x naught, increases with time. And this conducting bar is going to move at a constant or uniform velocity u. And in this case, the magnetic field B is static, but it is non-uniform. We can see from this expression for B that it's in the z direction like in the previous slide, but the B field gets stronger the further you go to the right. As x increases, the B field gets stronger. And you can see this is indicated in the diagram. These arrowheads that are pointing out of the page go from being very faint on the left to being very distinct on the right. This is how we're indicating that the B field is non-uniform. Let's also assume that this bar starts at x equals 0 at time 0. So it would be located right at the very left edge of this problem. and then it moves at a constant velocity once we start time at t equals 0. And so our question is to find the motional EMF between the terminals 1 and 2. So these are the terminals in our resistor here. So let's first begin by writing our motional EMF equation. So let's define a contour around which we're going to integrate here. So we know that we need to define motional EMF as the closed contour integral. So we'll use our symbol here, V EMF and then M for motional, as a closed contour integral of U cross B dot dl. With the motional EMF defined, we look at our picture again here, and we see that as we integrate about the closed contour C, there's a voltage developed across the resistor, which must be equal to the voltage developed across the sliding bar, because the rails on the top and the bottom don't contribute any motional EMF at all. So this is to say that the motional EMF that is going to be produced here is the same as the voltage that is developed across the resistor, which is the same as the voltage developed across our bar, which is V43. So to find V43, we just integrate from point 3 to point 4, the velocity crossed with the B field dot dl. So let's have a look at each of these components. We know that the velocity is constant, so we'll just call the constant u, and it is in the x direction. We have an expression for the B field already. It's circled in the paragraph above. And if we look at our dl element here, we're integrating in the y direction. So if we want to write an expression for dl vector, we could say that we are that's oriented in the y direction, and we can put a dy or dl here. Doesn't matter. Okay, so now we are ready to carry out this cross product and this integral. So let's evaluate the cross product first. So we have u x hat crossed with this expression for b, which is z hat b naught x. Again, remember, b is a nonlinear, non-uniform function of x. So we have to take this cross product of x hat and z hat. So if we think about a right-handed coordinate system, x, y, z, if I cross x and z, that's actually going to point in the minus y direction. So that's going to lead to something in the minus y direction. Let's write that down, minus y hat u b naught x. And then we're going to take that and we're going to dot that with dl, which we identified as y hat dy. So the dot product would disappear because we have two y hats, and we are now free to carry out this integration for the bar voltage. So we're going to integrate from point 3 to point 4, this quantity minus u b naught x dy. The integrand obviously does not depend on y, so when we integrate over y, if we look at our diagram, we're just going to end up with the length of the bar. So this is going to be equal to minus u b naught x times the length. And to match our diagram, I think x was being called x naught, so let's update that here. Okay, so this is the resulting expression for V43. We can go one step further because we realize that the position x naught is related to the velocity of the bar through this simple function here, right? Because we know that the velocity is constant, and so the position is a linear function of time, and at time equals 0, x naught was 0 as stated in the problem. So taking this forward, we can say that V43 is minus u b naught times u times t times L, which is minus u squared b naught t L. So we see that the voltage here is a linear function of time. If we were to plot the EMF or the motional EMF as a function of time, it is a linear function, as I just said. And this actually makes sense when we think about Faraday's law, and because Faraday's law says that we take the time derivative of the magnetic flux in order to find the EMF, and technically it's a negative of that. And our flux is increasing linearly with time because the area of this rectangular loop is increasing linearly with time. So in fact, we can go back and actually think about if we had tried to solve this problem using Faraday's law straight in order to get the EMF, we should get the same answer. So let's write out an expression for the magnetic flux. Let's remind ourselves what Faraday's law says. So Faraday's law says that if I take the closed contour integral of E dot dl, which is our EMF, this is equal to minus the time derivative of the magnetic flux, right? And there's only one term here, so we don't worry about flux linkage at all. So magnetic flux is the surface integral of B dot ds. So looking at our diagram, we are trying to integrate over the entire surface area of this loop. But we see that the area of the loop is a linear function of time, as I just mentioned, because x naught, the width of the rectangle, if you will, is a linear function of time. So let's write out our flux integral. It's going to be a double integral here of B naught times x z hat. This is the B field. Our ds element is just dx dy. Again, looking at our coordinate system here, you can see that I could make a little differential area element whose dimensions are dx by dy, and the surface normal to that differential area element would point in the z direction, so I can attach a z hat here. And then to integrate over x, I would integrate between 0 and x naught, which is the width of our rectangle, and the integral over y would be between its over its length. I could say maybe between 0 and L. The y position of the loop wasn't specified in the diagram, so we could establish an origin as shown here. All right, so the dot product of z hat is going to turn this into a scalar product, and so this integral is going to become, well, the integration over y, that nothing depends on y, so that's just going to integrate to L. And the integral over x, we have a linear function of x, so that's going to turn into a quadratic function of x, so we're going to end up with b naught x naught squared over 2 when we integrate over x. And we can write this because we have an expression relating x naught to velocity, so this is L times b naught times u times t squared over 2, and this is our total magnetic flux. Then, if we return to Faraday's law, which is written up above, our EMF should be the negative time derivative of this function. So we need to take phi and take its derivative and take negative of that result. So it's fairly easy to take the time derivative of the function above. We have a quadratic function of time. It's going to turn back into a linear function of time. So we're going to get L b naught 2 times u times t, and use the chain rule here to take care of the integral. And then we have this factor of 2 in the bottom, so these factors of 2 cancel out. And you see that we get the exact same result as the result from the motional EMF. Here's the motional result here. Here's the result just through direct application of Faraday's law. Of course, we wouldn't expect there to be any difference in the result. The motional EMF was derived from a different perspective in terms of magnetic forces on charges, but the net result obviously should be consistent with Faraday's law. So to summarize, we can go back and let's have a look at, we have this definition of the motional EMF, and I'm going to emphasize that here with a box. And I want to emphasize something here, that this is the general expression for motional EMF. But remember that when you're applying this expression, only the parts of the closed contour C that are in motion are going to contribute to the motional EMF. All the static parts of the contour don't contribute. And this leads us to our next example of an electromagnetic generator, which is shown here, where we have to employ that principle that I just mentioned. So let's describe the problem first. We have a closed loop, closed conducting loop, which is shown in red here, which is being rotated about the x-axis. And let's assume that the loop is centered on the x-axis so that it's not asymmetric. And we are going to try to find the induced EMF, or technically the motional EMF, if this loop rotates at a constant angular velocity, omega, within a constant magnetic field B. So again, the B field here is constant. So that means two things. First, B is uniform with space, doesn't vary like in the previous example. And second, B is not a function of time. It's constant with time. So we only expect the motional EMF to arise in this problem. There's not going to be any transformer EMF like in our previous examples because B is not a function of time. So let's write an expression here for B. Let's say, since it's uniform, let's just give it a constant value, B naught, and assign it to be in the Z direction. To analyze this problem more, let's draw a diagram of our loop from a few different angles. So the first angle we're going to consider is just the top view. So here's our loop looking from the top. And this is our top view. And the width of the loop is W. The length of the loop is L. And we can superimpose our coordinate system if it's clearer, like so. So this is the Y direction here and the X direction here. So we're looking down the Z axis. The Z axis is coming out of the page. And so if we were to write our B field, we would write it as a series of arrowheads coming out of the page like this, and it's uniform. So this is our loop, and in order to find the EMF, we're going to have to integrate about this contour. And to make that a bit clearer, let's attach some labels to the vertices of this loop, 1, 2, 3, and 4, just so that it clarifies things in the ensuing discussion. Let's also draw a side view of our loop. So let's look at the loop down the x-axis. So if we look down the x-axis, so if we were looking over here and we look down the x-axis, then we would see the z, y axis like shown here. And let's draw the loop at a particular position here. Like it is rotating, and so let's say that the loop had assumed this particular position here, and the loop was in red, so maybe I'll make this red just so that it's clear that this is the loop. And here are the two ends of the loop going into the page. So at any given time, we can draw a surface normal to this loop. Let's draw it like this and call this n hat. And this surface normal, let's say that it makes an angle theta with the z-axis. Okay, so this part of the loop wants to rotate this way, and this part of the loop wants to move the other way. Now, when we define the angular velocity omega, which is shown in the diagram on the left, omega is the rate of change of angle theta with time. So this is d theta by dt. And we've been told that omega is a constant. So if we integrated this expression, the angle theta would be simply omega t plus some constant of integration. And to simplify things, let's just say that theta was 0 at time equals 0, so that we don't need to worry about this constant. Okay, so this loop is going to turn around. Now, remember when we defined the motional EMF, we said that only the segments of the loop or the contour that cut through the B field contribute to the motional EMF. Thinking to our previous example, only this bar is cutting through the B field, like the B field's coming out of the page and it's literally cutting those vectors as it slides from left to right, whereas the rest of the circuit was constant or not moving. So here, let's think about which segments of our loop cut through the B field as the loop rotates. There's actually only two segments that do that. The segment 1, 2 cuts through the B field. You can imagine this thing rotating and slicing the B field. And the segment 3, 4 cuts through the B field. But the segments 2, 3 and 1, 4 are not cutting through the B field at all. So we don't expect any motional EMF contribution from those segments. So let's write that down because that's a fairly important point. Only the segments 1, 2, and 3, 4 cut through the B field. Okay, so only they will contribute. So let's analyze segment 1, 2. So we will focus in on one particular segment, 1, 2. And it moves with a velocity, right? It moves with a linear velocity, which must be related to the angular velocity that the loop is rotating at. And we can find that linear velocity by taking the moment arm, and you may recall the definition of moment arm when we talked about torque before, and multiplying this by angular velocity. So let's return to our side view picture up above here. Our moment arm, so this is the segment 1, 2 up here, right? So our moment arm is this segment here, right? Because the loop is rotating about the x-axis, so the center of the loop is along the x-axis, and segment 1, 2 is rotating about the x-axis, and the distance that segment 1, 2 is from the x-axis is the moment arm. So the length of this moment arm is W over 2. And if we want to, so this is going to be at this particular moment in time, this wire is moving at a linear velocity in the direction I've just sketched there, which is the product of the moment arm and the angular velocity. And you can see it points in the same direction as the n hat vector that was sketched in red in the side view. So let's write that down. We can write this velocity as u12 times w over 2 times omega, the angular velocity, times n hat. So now we have an expression for velocity to be able to apply in our motional EMF equation. So this linear velocity for segment 1, 2 is actually the same velocity that segment 3, 4 has, except that segment 3, 4 goes in the minus n direction at this particular instant in time. So we might as well write the velocity for segment 3, 4 because we're going to need it when we calculate the total motional EMF. Now we can calculate the motional EMF, and to do that we need to identify a contour over which we're going to do that, or at least a direction of the contour. And so I'll sketch this in green here. Let's compute this contour in the counterclockwise direction. Integrate counterclockwise. So again, only segments 1, 2, and 3, 4 will contribute, but when we consider this particular direction of the contour, we can see that we're going to have to integrate from 2 to 1 for segment 1, 2, the cross product of u12 crossed with b dot dl12, let's call it that, and sorry, we're integrating from 2 to 1, so maybe I'll call this 2, 1. And we can see that that's actually in the x direction, and the top and the bottom don't contribute. And then when we integrate over the second moving bar, we will integrate from 4 to 3, the velocity u34 crossed with b dot dl43. So realize that dl43 is actually in the opposite direction as dl12. Okay, so let's evaluate this integral now. Let's consider just this portion here first and evaluate that. So let's substitute in everything that we have. So we're integrating from 2 to 1. U12 we have an expression for, it's W over 2 times omega n hat. And then we're going to multiply this by B naught Z hat. And then we're going to take the dot product of this with our DL12, which we can see is in the x direction and has a length dx. Okay, so we're just looking at the first term here. Now let's deal with this product of n hat crossed with z hat. So if we return to our side view diagram, you can see n hat points up and to the right and the z-axis is upward. So if I evaluate n cross z hat, the result is going to be in the positive x direction. And the magnitude of the cross product of these two unit vectors will be the sine of the angle between them. So this will be equal to x hat sine theta. And then we're going to end up dotting these two x hats together, which will just get rid of our dot product in this expression. So writing a simpler expression for this, we can see that if we integrate this expression, we're integrating with respect to x. X doesn't appear anywhere in our expression, so we're going to end up with the length of the segment from 1 to 2, which in our diagram was labeled as L. Right? So the result of this will be L times W over 2 times omega B naught sine theta. That's going to be the contribution from segment 1, 2. And actually, the segment from 4, 3 or 3, 4 is actually going to be the exact same value because the velocity is in the opposite direction. So U34 is opposite to U12. So this guy is inverted relative to U12, but the direction of integration is also the other direction. So these two negatives will cancel and make a positive. And so if we can consider the contribution from the other segment, it will add to this as well. And basically, when we sum these two together, we'll get rid of the factor of 2 that you see in the denominator. So our total motional EMF is going to be equal to W times L times omega B naught sine omega t. And here I've substituted omega t for theta. So now we can see the time dependence of our EMF. If we want to plot the EMF as a function of time, it's shown here. So let's put the EMF on the y-axis, and let's just put omega t on the x-axis here. We're going to sketch out a sinusoidal function of time. The peak value is going to be this product of W, L, omega, and B naught, and that will also be the negative value here. And this repeats every 2 pi, considering that we're plotting against omega t. So this is alternating current. And this is the basis for all electromagnetic generators. The simplest one that we've shown here, if I just take a plain loop of wire and rotate it around a constant B field, which could be established by an electromagnet operating under direct current or even a permanent magnet, then turning that loop around would produce a voltage within the loop or an EMF within that loop, which has got this sinusoidal variation with time. Now we're able to define total EMF, having gone through motional EMF. And I mentioned at the very beginning of the lecture that the total EMF is simply the sum of the transformer EMF and the motional EMF. So total EMF is what we observe by integrating E dot dl around our closed circuit. And this is equal, by Faraday's law, to be equal to minus d psi by dt, again assuming only one turn in our loop. And the right-hand side can be broken down into our transformer EMF. So let's just substitute in the expressions that we had previously for that. The transformer EMF is the surface integral minus the surface integral of the partial derivative of v with respect to time. That was our expression for transformer EMF. And then the motional EMF, which has been our focus today, is the closed contour integral of u crossed with b dot dl. So we can always write Faraday's law in this way. We can decompose the contributions to the total EMF into a transformer contribution and a motional contribution.